In this section, we're going to be looking at procedures for making inferences about a population mean when we don't know the population variance, we don't know the population standard deviation. So suppose now that sigma squared, the variance of the population from which we're sampling and about which we want to draw inferences, that variance is unknown. And obviously, if the variance is unknown, the population standard deviation, sigma, is unknown as well. So since sigma is unknown, we're not able to calculate this standardized version of x bar that we were utilizing in the previous section to make inferences about mu. Right? We can't calculate the denominator, and so we can't calculate this. Now, we do have an estimate of sigma squared, namely s squared, the sample variance. And if we replace sigma squared by s squared in this formula, we get the following expression, which is now something that we can compute. And so this new expression, which we're going to denote by lowercase t, is x bar minus the population mean divided by, and then the quantity in the denominator is now not the true standard error of x bar, but it's the estimated standard error of x bar. Because see, we don't know the true value of the standard error of x bar because we don't know sigma squared. So the denominator in this ratio is the estimated standard error of x bar. And so we can represent it as the square root of the sample variance over the sample size. Or if we pull the sample variance out, we have to take its square root, and we get the sample standard deviation s over the square root of the sample size. So this is a statistic that we can compute, and it turns out that when we replace sigma squared by s squared, the resulting expression, the resulting random variable, no longer has a standard normal distribution. It has what's called student's t-distribution. Now, if I were to show you a graph of student's t-distribution, you might say, well, that looks exactly like a standard normal distribution. It's centered at the same place, it's bell-shaped, it's unimodal and symmetric. But if we were to superimpose the standard normal and the t-distribution on top of it, then you would see that the t-distribution is somewhat wider. And what that means is, or what the reason for that, is that this random variable that we're calling t has two sources of variation driving its variability rather than just one, which is the case for z. If we look at this formula for z, the only random variable in this expression is x bar, which is in the numerator. On the other hand, if we look at the expression for t, we have not only x bar in the numerator, but we have the sample standard deviation in the denominator. And so we've got these two sources of variation that are causing this random variable to vary, and for that reason, student's t-distribution is a little bit wider than the standard normal. Now, associated with the t-distribution is a parameter called degrees of freedom. And in this context, the number of degrees of freedom associated with this distribution is equal to n minus 1, one less than the sample size. Now, whereas for the standard normal, there's only one standard normal that we deal with. When we talk about the t-distribution, there are actually an infinite number of t-distributions. And there is a t-distribution for every possible degrees of freedom. And the degrees of freedom would range from the positive integers. So when we're dealing with the t-distribution, we have to know how many degrees of freedom we're talking about. And like I said, in this context, in the framework for making inferences about a single population mean, the number of degrees of freedom is n minus 1, sample size minus 1. So knowing that the sampling distribution of this random variable that we're calling t has a student's t-distribution, this knowledge provides the basis for constructing hypothesis tests and confidence intervals for a population mean. So let's take a look at what we can do. So let's look at the hypotheses. So we've got, again, three hypotheses. A two-tailed test, which is I'm labeling hypothesis A. We have a left-tailed test, which I'm labeling hypothesis B. And we have a right-tailed test that I'm labeling hypothesis C. So we have the same 3 tests, and I'm labeling them in the same way as we had in the previous section where we assumed that we knew the population variance and standard deviation. But now notice that in the notes here you can see that we're specifically saying that the population standard deviation is unknown, which in reality is the more realistic situation. It would be very unusual for us to know what the variance or standard deviation is in a population in a real situation. Okay, the test statistic that we're going to use is very similar to the test statistic that we used in the previous section. The only difference is that now, instead of having sigma squared or sigma down here in the denominator in the formula for the test statistic, which we can't use, remember, because we're now considering the situation where we don't know the population variance or the population standard deviation. So in the denominator of the test statistic, we now have, and I'm pointing to the version on the right-hand side here, we have the sample standard deviation in the denominator. So the test statistic formula is the sample mean x bar minus the hypothesized value of the population mean, which I'm denoting by mu naught, and then I'm dividing that difference by the estimated standard error of x bar, which is the sample standard deviation over the square root of the sample size. And again, if the null hypothesis is true, so that mu is equal to mu naught, then this test statistic, which we're calling t-calc, has students' t-distribution with n-1 degrees of freedom. And so we can use that information to come up with the rejection criteria for the test. And so if we are performing a two-tailed test, hypothesis A, then we are going to reject the null hypothesis if our test statistic t-calc is either small or if it's really big. Now, how small or how big does it have to be? Well, if t-calc is strictly less than this quantity here, negative t sub alpha over 2 comma n minus 1, or if t-calc is greater than this value, t sub alpha over 2 comma n minus 1, then we will reject the null hypothesis. If we're performing a left-tailed test, so hypothesis B, then we're going to reject for small values of our test statistic t-calc. In particular, we're going to reject the null hypothesis if t-calc is strictly less than negative t sub alpha comma n minus 1. And if we're performing a right-tailed test, hypothesis C, then we're going to reject the null hypothesis if our test statistic t-calc is large. In particular, if it's greater, strictly greater than t sub alpha comma n minus 1. Now, again, what are these t values here? Well, these are very similar to z values. So for example, t sub alpha comma n minus 1 is defined to be the upper alpha percentage point, not of the standard normal distribution, but of the t distribution with n minus 1 degrees of freedom. So notice that in the subscript here, not only do we have the right tail area, which I'm denoting by alpha here, but we have to specify the number of degrees of freedom because we have to identify the particular t-distribution that we are talking about. Now obviously, if I look up here in the upper critical point for the two-tailed test, hypothesis A, the upper critical point is the upper alpha over 2 percentage point of the t-distribution with n minus 1 degrees of freedom. Now let me stop here and just say a few words about the t-distribution and the t-tables that you've got on the Moodle and in your course packet, and in particular the structure of the t-table. So let me bring that up, and the tables that you have, the t-table that you have in the course packet and also on Moodle is 4 pages long, and here I'm just going to look at the first page. You'll notice that the structure of this table is different than the standard normal table, and the reason is we've only got one standard normal table, but we've got an infinite number of t-distributions. Now obviously we're not going to be looking at all of them. We can only look at a certain number, but notice here that in the first column, and then for convenience also in the last column, I've got a column, these columns are labeled DF for degrees of freedom, and so these correspond to the degrees of freedom for the t-distribution that we happen to be talking about. And so on this first page, notice that the degrees of freedom range from 1 up to 50. All right? And also notice that if you think back to the standard normal distribution, the body of the table contained right tail areas, at least in alternating columns. In the t-table, that's not the case. In the t-table, right tail areas are given across this top row. And you can see here in descending order, the right tail areas that we provide for range from 0.25 to 0.1, 0.05, 0.025, 0.01, 0.005, 0.001, and 0.0005. So these are all right tail areas that are commonly used right tail areas, and that's why they're provided. Then what's given in the body of the table are the values on the horizontal axis, or the number line, to the right of which, under the corresponding t-distribution, give us the corresponding right tail area in that first row. So for example, if we were to want to know the point on the number line that gives us a right tail area of 0.05, to the right of that point, underneath the t-distribution with 10 degrees of freedom, we would go down to the row corresponding to a t-distribution with 10 degrees of freedom, and then we would look for the column for the right tail area we want, in this case 0.05, and we would see where they intersect, and we see here that the point of intersection in the table gives us a value of 1.812. And so the 1.812 is the upper fifth percentage point for the t-distribution with 10 degrees of freedom. In other words, if you were to draw a graph of the t-distribution, and then draw which is going to be centered at 0, by the way, and then draw or identify the point 1.812 on the number line, then the area under that t-distribution with 10 degrees of freedom to the right of 1.812 would be 0.05. All right? So that is how the t-table works, and you do have a handout of practice problems for the t-distribution, and the solutions are out there. And so I would highly recommend that you get some practice using the t-distribution. It is slightly different than using the standard normal, but I think you'll get the hang of it pretty quickly. All right, so let's continue on going through the notes here and seeing how we do these hypothesis tests when we don't know sigma. So we have specified the rejection criteria, and then we also have formulas for calculating the p-value for the test. So remember that we can, in drawing conclusions about a population mean using a hypothesis test like this, we can either use the test statistic combined with the rejection criteria, or we can use the p-value and compare that to the significance level. Both ways, they're both equivalent. They'll give you the same qualitative result, the same decision, but we do need to know how to use both because p-values are typically used in the literature. So if we're performing a two-tailed hypothesis test about a population mean, then the p-value using a t-test, the p-value is twice the probability that a t-random variable with n-1 degrees of freedom is greater than or equal to the absolute value of t-calc, the test statistic for the test. If we're performing a left-tailed test, then the p-value is equal to the probability that the t-random variable with n-1 degrees of freedom is less than or equal to the value of t-calc that we obtained. And if we're performing a right-tailed test, then the p-value is equal to the probability that the t-random variable with n-1 degrees of freedom is greater than or equal to t-calc. Again, as we saw when we were using the z-test, for the t-test here, notice that in the formula for the p-value for a two-tailed test, we're taking the absolute value of t-calc, whereas we're not taking the absolute value in the left-tailed test or the right-tailed test calculations for the p-value. Okay, so this is the procedure for performing a t-test for testing hypotheses about the single population mean. You'll see that, this is very, very similar to using the z-test for testing hypotheses. Really, the only differences are in how we calculate the test statistic and in the reference distribution that we use to get the critical points. And for the t-test, instead of getting our critical points from the standard normal distribution, we get them from the appropriate t-distribution. But overall, the approach, the overall procedure is very, very similar. So I think this is a good place to stop. In the next video, we'll look at some examples of the t-test. So see you in a few minutes.